Hello, everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter P block elements and we'll be continuing with group 14 elements. We have talked in detail about carbon in the last few lectures, and in this particular lecture, we will be covering silicon. That is the second element of this particular group, and we'll be discussing in detail about the various properties, preparation, etc., abundance, etc., everything that is related to silicon. Before we begin, a piece of information for you. You can use the coupon codes Mission J or Mission NEET while you enroll at First Online University for Mission J or NEET in order to avail good discounts. Let us now begin with silicon. Okay, so this is going to be a bit lengthy lecture, but this is going to cover everything that is important from examination point of view as far as silicon is concerned. Now, silicon has the symbol Si, right? Its atomic number is 14. The atomic weight of it is 28.0855 atomic mass units. Now, what are the important compounds of silicon that we have to discuss in this particular lecture? We'll be discussing silicon dioxide, that is SiO2. Silicons, what are silicons? What are silicates? We'll be covering everything. First of all, let's discuss the simplest compound of silicon, that is silicon dioxide. Now, 95% of the Earth's crust is actually made up of silica, that is silicon dioxide. So, silicon dioxide, that is SiO2, is commonly known as silica and silicates also. Okay. Silica has crystalline as well as amorphous allotropes. The crystalline forms are quartz, cristobalite, and tridymite, whereas the amorphous forms are jasper. The pictures are being shown to you alongside onyx. This is what it looks like, and agate. Okay. Now, silica is a covalent three-dimensional network solid. If you carefully under a microscope or whatever, like not under a microscope, if you look at the structure of silica, you're using XRD, that is X-ray crystallography, you will see that it is actually a three-dimensional network solid, and it looks like this. Actually, looks like this. Each silicon is going to be bonded. If you look at that structure, you will find that each silicon atom is bonded to 4 other oxygen atoms in a tetrahedral manner. So there is silicon in between, and the 4 oxygen atoms which are bonded to the silicon atom are actually in a tetrahedral manner by covalent bonds. Each oxygen atom is bonded to 2 silicon atoms. So if you see this three-dimensional network structure, you will see that each silicon is bonded to 4 oxygen atoms in a tetrahedral manner, and each oxygen atom is bonded to 2 silicon atoms in a linear manner. The entire crystal is a very huge giant molecule in which we have 8-membered rings being formed, and they are formed with alternate silicon oxygen atoms. So if you look at this structure, you will see that the silicon oxygen atoms are alternating with each other. We have already seen. Now, carbon dioxide exists as a Okay, so I thought there was this bubble from the carbon dioxide lecture here. No, silica is being compared to carbon dioxide. So CO2 and SiO2. Now CO2 is a gas because the CO2 molecules are very small and there are weak van der Waals forces of interaction existing between them. But when I talk of SiO2 exists as a solid because it has a giant molecular structure because of the three-dimensional tetrahedral network that exists. SiO2 is almost non-reactive because the SiO bond enthalpy is very high and it is very difficult to break this SiO bond. Therefore, its reactivity is low. However, it can be attacked by two substances. One is hydrofluoric acid, that is HF, and the other is sodium hydroxide, that is NaOH. Hence, we can say that HF cannot be stored in a glass vessel because glass is nothing but quartz. Quartz is nothing but silica. So, therefore, HF cannot be stored in glass vessels. And in order to avoid the attack of HF on glass materials, we store it in plastic bottles. Similarly, silica on reaction with NaOH will form sodium silicate, which is again called water glass. And silica with HF will form fluorosilicic acid. Hydrofluorosilicic acid H2SiF6. Now note that silica is not soluble in acids like H2SO4 or HNO3. It will only be soluble or it will only react with hydrofluoric acid, that is HF. So SiF4 with water will form H4SiO4 and H2SiF6, that is hydrofluorosilicic acid. Now, let us talk about the crystalline allotropes of silica first of all. When we talk about quartz, quartz is used in the manufacture of accurate clocks, quartz clocks, okay? Then in modern radio, it is used, in television broadcasting, it is used, and radio communications also. Then when we talk about silica, silica is used as a dehydrating agent and it is also an adsorbent in chromatography. You must have heard of thin layer chromatography, TLC. In TLC, what we have is that column is actually made up of silica only, on which the adsorbate is going to travel. So it acts as the adsorbent, and the adsorbate, depending upon its RF value or its solubility in that particular solvent, will travel onto this silica phase. Then Kieselguhr, which is the amorphous form of silica, it is used in filtration plants also. This is the Kieselguhr. I'm not really sure about the pronunciation. This is the filtration that we have. Now, based on this, let's quickly have a look at. So we'll be dividing this lecture into a few sections and we'll have concept check questions after each of the section. Okay. Now let's see a few MCQs. The formula of silica is Si, SiO, SiO4 minus or SiO2. Very simple. It is SiO2. So option D is the correct answer. Next question is, what is the structure of silica? Three-dimensional, tetrahedral, linear, octahedral, pyramidal. We have seen that it is tetrahedral three-dimensional network structure. So option A is the correct answer. Next question is, which of the following is not stored in glass vessels because it reacts with glass? It is HF. Hydrofluoric acid. Option B is the correct answer. Next we move on to, so this was all about silica or silicon dioxide. Next we move on to silicons. Now what are silicons? Silicons, as is clear from the name, these are actually organosilicon polymers containing repeating units R2SiO, which are held by SiO-Si linkages. So what we have is SiO-Si linkages and we have organosilicon polymers. These organosilicons means you have SiO-Si linkages. Apart from that, you also have some organic moiety which is attached to this silicon atom. What is the empirical formula? Empirical formula is R2SiO. This is how it will look like. So SiO linkages are there, but at the same time, the silicon atom will also have two of the R groups attached to each silicon atom. Now here R could be alkyl like a methyl group or aryl also like a phenyl group. Like you can see this polydimethyl siloxane where there is an SiO-Si linkage, but there is also two methyl groups which are attached to each silicon atom, and the repeating unit is actually SiCH3CH3O. Okay, therefore it's forming a polymer. Similarly, you can also have polydiphenyl siloxane where you will have, instead of methyl groups, phenyl groups attached to each silicon, two phenyl groups attached to each silicon atom. So what are silicons? Silicons are simple silicons consist of SiO and then there are two R groups which are attached to silicon N unit. Okay, the monomer is SiO and two R groups attached to silicon. These are the chains in which the alkyl or phenyl groups are occupying the remaining bonding positions on each silicon. They are hydrophobic, that is water repellent in nature. Okay, they are going to be insoluble in water. Now, what are the various types of silicons? Silicons can be short chain, which are like only the oily ones. Okay, I mean they exist only in the form of oils. Then you have medium chain, which are viscous oils, jellies, and greases, as you can see in the picture. And then we have long chain silicons, which are actually in the rubbery elastomers or resin forms, as you can see in the picture. Okay, the swimming glasses that you wear, these and the pipes, various pipes which are like, elastomers like material, these are all silicons only. Now, how are silicons prepared? The starting material for the manufacture of silicons are either alkyl or aryl substituted silicon chlorides. Okay, so RnSiCl 4 minus N, that is the formula for substituted silicon chlorides, aryl or alkyl substituted. And what do we do is that methyl chloride is going to react with silicon in the presence of copper as a catalyst, and the temperature is 573 Kelvin in order to form methyl substituted chlorosilicon, because we are taking methyl chloride, so we'll get methyl substituted chlorosilane. Now, hydrolysis of dimethyl dichlorosilane, that is, you will have 2 methyl and 2 chloro attached to silicon, followed by the condensation polymerization, that is, removal of a small molecule like water or ammonia, is going to give straight chain polymers. RSiCl3 is used for the preparation of cross-linked silicon, and the chain length of silicon polymer can be controlled by adding R3SiCl. We'll have a look at this process. So if you look at step 1, the step 1 in polymerization, we have 3 steps: chain initiation, chain propagation, and chain termination. So if we look at step 1, that is chain initiation step, what we have is silicon is going to react with methyl chloride, and what we get is dimethyl silane. Okay, and now condensation, for condensation polymerization, we need to remove some small molecules. Say we are adding water and we are removing HCl, so what we'll get is CH3 remains as such, and in place of Cl, 2 Cl atoms, we'll have 2 OH moieties. So what do we get is dimethyl silane diol, or you can call it as dihydroxy dimethyl silane. Now, the step 2 is propagation. Now, once we have formed the monomer, now it is important that these monomers go on linking with each other in order to form a long chain polymer. So, when we have got this dihydroxy monomer, 2 monomers will combine together and water is going to be removed from here. And what we will see is the formation of this particular polymer, which are nothing but silicones. So this is how the propagation dihydroxy dimethyl silane molecules will combine together to form a long chain polymer. Now, once we have the chain propagation taken place, now it is important that we terminate this chain. And the third step, therefore, in the polymerization reaction is chain termination. How do we actually stop this chain from growing further? Because there is one particular length of the polymer that we require. So the chain growth of the polymer can be controlled by adding chlorotrimethyl silane that I was just talking about in the last to last slide maybe. So when we have this polymer being formed and we add ClCH3 whole thrice Si to it, what do we get is HCl getting removed, and ultimately what we have is the polymerization is going to stop with the formation of silicones. Okay, this is how we get one particular length of a silicon that is actually desired. Right. Now, what are the uses of silicons? We have talked about the preparation of silicons. Now we need to move on to why do we need silicons at all? Okay, for that we need to know what are the uses of silicons. Now, silicons are used in textiles and in order to prepare waterproof papers. Okay, umbrella material, and the papers which are waterproof are actually made up of silicons. Then they are also used as lubricants at both high and low temperatures because they are oily in nature, right? Then silicons are also used as sealant in order to seal. If you want to, there is some leakage or something and you want to seal it, you can make use of silicons. They are also used as greases in order to apply grease to some particular, say any opener or anything like that in order to, control its opening and closing technique. Then electrical insulation is another use for which silicons are actually used. Now, because of the biocompatibility of silicons, they play an important role in surgical and cosmetic plants also. Okay. Now, based on this, we have studied in detail about silicons. Now, we need to look at certain questions based on silicons. What is the general formula of silicons? R2SiO, R2SiO2, RSiO2, and RSiO. We have seen it is R2SiO. So, option A is the correct answer. Next question is, which of the following is used to terminate the chain polymer? So we have seen that it is CH3 whole thrice SiCl. Okay, trimethyl chlorosilane. So option B is the correct answer. Next, we move on to the last topic or the last important compound of silicon that we have to discuss, that is silicates, and that will also include the concept of zeolites. Now, when I talk about silicates, what are silicates? Do not get confused between silicons and silicates. These are two different, very different. See, silicon dioxide, you will not get confused in silica or silicon dioxide is one complete different thing. Now, when we are talking about silicons and silicates, we need to look at or we need to understand the difference between the two and how do we not get confused between the two. So, when I talk about silicates are basically oxo anions of silicon, that is SiO4 4 minus, that is oxo anions, means they contain oxygen and they are existing in the anionic form. So SiO4 4 minus units, they form a tetrahedral geometry. Wherever you see SiO4 4 minus unit, you will see that it is a silicate. Now, what are the sources of silicates? We have rocks, we have clay, soil. All these are important sources of silicates. A large number of silicate minerals also exist in nature. Some important minerals are feldspar, okay, mica, zeolites. Now, zeolites are very, very important that we're going to discuss. Asbestos, that's also an important silicate mineral. Now, what is the structure of silicates? We have seen that it is SiO4 4 minus unit and it has a tetrahedral geometry. So the basic structure unit is SiO4 4 minus. How does it exist? So we have one silicon atom in between and we have four oxygen atoms attached to it, each one having a negative charge. So it's going to be a silicate, basic structural unit. So the types, depending upon the number of corners of SiO4 4 minus units, shared silicates are classified. So the number of corners shared, silicates are going to be classified as orthosilicates, pyrosilicates, chain silicates, sheet silicates, and 3D silicates. Let us have a look at all of these one by one. So when I talk about orthosilicates, in orthosilicates, we have Si4 plus atom in between. I mean Si4 plus cation in between, and we have the four oxygen atoms which are not being shared. Okay, so simply SiO4 4 minus is orthosilicate. But when we have one oxygen atom being shared between two SiO4 4 minus units, ultimately giving it Si2O7 6 minus charge, that is called as pyrosilicates. Okay, then when we have, these units, so when it's just two SiO4 4 minus sharing one oxygen, it is pyrosilicates. But when it goes in a chain-like manner, that so many SiO4 4 minus units are sharing one oxygen each, we call it as chain silicates because they are forming chain. Then when these chains are going to exist as single chain or double chain or multiple chains which are attached to each other to form a sheet, we call it as sheet silicates. And lastly, when they are going to have three-dimensional structure, we are going to call it as 3D silicates. Simple to understand. Now, two important man-made silicates are also there. One is glass, the other is cement. Okay, so glass and cement are the two most important man-made silicates. Very, very important information to remember. You can be asked a direct MCQ on this. So orthosilicates SiO4 4 minus, pyrosilicates Si2O7 2 minus, chain silicates SiO3 whole N 2 minus, cyclic silicates Si3O9 6 minus. Sheet silicates, we have three oxygen atoms of each SiO4 tetrahedral units being shared. Then framework silicates, we have four oxygen atoms of each SiO4 tetrahedral units being shared. So this is one information. I mean, this is like so much information in just one sheet of paper that you can actually jot down and revise it again and again because this is very, very important. Now we move on to zeolites and how are silicates actually associated with zeolites. So when we talk about zeolites, the Greek word zine means boiling and lithos means stone. So zeolite, if aluminum atoms replace a few silicon atoms from a three-dimensional network of silicon dioxide, that is SiO2, the overall structure will be known as aluminosilicate, which acquires a negative charge. because silicon is actually 4 plus and aluminum is 3 plus. So there is one positive charge that is left, which will have to be neutralized by an extra negative charge. So overall, there is going to be one negative charge. So cations such as Na plus, K plus or calcium 2 plus are going to balance this negative charge. So when you talk about SiO4 4 minus unit and one of the Si4 plus being replaced by Al3 plus, then what you get is, so if you look at pure silica versus silica having one metal atom being present there in order to neutralize the negative charge that is present, that is nothing but, so when you have two silicon atoms, the that is pyrosilicate that we have discussed is a simple pure silica. But when one of the Si4 plus is going to be replaced by Al3 plus, giving an overall negative charge, which requires a cation to balance or neutralize that negative charge, that structure is known as zeolite, as you can see in this picture. Okay. So we have pure silica and that versus zeolite, which has one silicon atom replaced by aluminium 3 plus. So there is a negative charge which is going to be balanced by the metal ion. For instance, we have sodium zeolite, means sodium is present as the neutralizing cation. So Na2O, Al2O3, Al2O3 will be present along with X moles of say SiO2 and Y moles of say water. So this is going to be the formula for sodium zeolite, where X could be ranging from 2 to 10 and Y could be ranging from 2 to 6. Now, what are the various types of zeolites? We have natural zeolites and we have synthetic zeolites, as you can see in this picture. Now, what are the applications? Very important part is the applications of zeolite. It is used for the cracking of hydrocarbons and also for isomerization. ZSM5, that is the most important zeolite, which is used to convert alcohols directly into gasoline. This is a very, very important application. Then hydrated zeolites are used as ion exchangers in softening of hard water. Now, when I talk about fuel gases, fuel gas, let's look at various fuel gas, their composition and calorific values. When I talk about water gas, that is CO plus H2, which is also known as synthesis gas, has the composition 40 to 50% carbon monoxide and 45 to 50% H2. And it has a calorific value of 13,000 kilojoules per metric cube, which is an endothermic process. Then we have producer gas, which is 33% carbon monoxide and 64% N2, and whatever remaining 1% is, that is actually carbon dioxide and H2. The calorific value is 5439.2 kilojoules per metric cube, and it's an exothermic process. Then we have semi-water gas, which is carbon monoxide plus N2 plus H2 plus methane. Calorific value 7524 kilojoules per metric cube. See, calorific value might not be so important, but the composition and the fuel gas name are very, very important. You need to learn that. Next, we have carbureted water gas, which is carbon monoxide plus H2 plus few hydrocarbons. When we talk about what is calorific value, so if we, the order of calorific value, then the coal gas will have more calorific value than carbureted water gas, which will have more than water gas. Coal gas and water gas will have H2 as the major gas present. Then water gas has more than semi-water gas, as is clear from the name, which will have more than producer gas. And N2 gas in semi-water gas and producer gas, N2 gas is the major gas that is present. So towards the end of the lecture, let's quickly have a look at few MCQs based on silicates. The structure of silicates is linear, angular, square planar or tetrahedral. It is tetrahedral. Option D is the correct answer. Next question is, what are zeolites? Aluminosilicates, boron silicates, beryllium silicates or magnesium silicates. We have seen that when one of the SiO4 plus is going to be replaced by Al3 plus, what we get is zeolites. So these are aluminosilicates. Option A is the correct answer. Next question is, zeolites are negatively charged, positively charged, neutral species, all of the above. See, originally zeolites are negatively charged. We require a cation to neutralize it. So option A is the correct answer. Lastly, zeolites are used in cracking of hydrocarbons, yes. As ion exchangers and softening of hard water, yes. In isomerization of hydrocarbons, yes. So, in the conversion of alcohols to gasoline, yes. So, all of these, A, B, C, D, option 4 is the correct answer. So, this is all about silicon that is important from examination point of view that we have to discuss. And all the things that we have discussed in this lecture are very, very important. You need to be very clear with the concepts, and whatever is required to be memorized, you have to do that. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.